Hello everyone, this is Dr. Lennon, and today we're going to talk about inflection points. So a point at which the graph of a function changes concavity is called an inflection point. So we've seen that before from graphs. So, an example of such a graph, maybe you could look at like a cubic polynomial. And we have, somewhere about here we see the shape of the graph changes from that downward U shape to that upward U shape. So that point there would be our inflection point. So the indicated point is an example of an inflection point. Because the graph changes from concave down to concave up. So, the graphical notion of this is nothing really new for us, but what we are going to look at more is, suppose we have a function. Can we look at the function and the formula for the function and use the derivative to figure out whether or not we have an inflection point? And so, yeah, the answer would be yes. Basically, how does this work? Well, we can say if f double prime of p, so if you plug in an x value into the second derivative and you get something that's either 0 or undefined, then we can say that p is a possible inflection point. So we don't know whether or not it is, but we know it's a candidate. So what you have to do is we have to do something similar for critical points. So to test if P is in fact an inflection point, check to see if the second derivative changes signs at P. So let's go ahead and look at such an example. So this will kind of recap a little bit of what we were doing last time as well. So let's say find all critical points and inflection points for f of x equals x cubed minus 9x squared minus 48x plus 52. So to find the critical points, we take the first derivative, set that equal to 0, and solve. So let's go ahead and do that. So the first derivative, f prime of x, would just be 3x squared minus 18x minus 48. We're just applying the power rule. The derivative of 52, the constant on its own, is 0. So what we want to do is we want to set that equal to 0 and try to solve it. And we notice that all of those numbers are divisible by 3, so we can start by factoring out a 3, and we get 3 times the quantity x squared minus 6x minus 16. And so then that trinomial can be factored as well. So that factors into 3 times x minus 8 times x plus 2. So we get two candidates for our critical points, x equals 8 or x equals minus 2. And remember, essentially what we're doing is we're just dividing up the number line into some pieces based on those values. So we have negative 2 and 8. And we're plugging sample points from each region in to the first derivative here to see if we get something that's positive, negative, or zero. Positive or negative. The only places it's going to be 0 is negative 2 or 8. So region 1, region 2, region 3. We want to know, is the first derivative bigger than 0 or less than 0 in these regions? So the easiest region to test is region 2. Again, we're testing, so test critical points here. So if you plug in 0 into that function, you would get negative 48. So we know that this would be less than 0. If you would plug in something like negative 3, so we could include the sample points, e.g. f of 0 is minus 48. And then I think the other regions both end up being 0, but let's double check by plugging in a point. So region 1, maybe we plug in negative 3. And if you plug in negative 3 into the derivative, what do you get? You get negative 165. Oh, did I? Oh, no, you get, sorry, I messed that up. 3 times negative 11 times minus 1, we would get positive 33. So f of negative 3 is positive 33. And in the last one, we could plug in just some number bigger than 8. So maybe we plug in 9, and we would get positive 33 there. So what does that tell us? Well, remember, these are both critical points, and it basically tells us from the first derivative test, we change from increasing to decreasing, and then decreasing to increasing. So from last time, we know that a local max occurs at x equals minus 2, and a local min occurs at x equals 8. Okay, so that's first derivative test stuff. If we go back up, we can perform something similar to find the inflection points. So trying to find the inflection points, we would start with the second derivative. So if you take the derivative of the first derivative, you would get 6x minus 18. So we test for inflection points here. So that's the function we test inflection points for. But we set that equal to 0 and solve. So we get 18 is equal to 6x. Divide by 6, we get x equals 3. So I write 3 equals 3. Well, that's true. That's not what I meant to write. So x equals 3. So now we have, again, a number line, but we're testing in the second derivative to see if things change signs here. And that will tell us whether or not indeed we have an inflection point. So in region 1, we could test, say, 0. So f double prime will end up being less than 0. So e.g. f double prime of 0 is equal to minus 18. Region 2, the second derivative is going to be positive. So we could test maybe 4. So f double prime of 4. What does that come out to? That comes out to 6, which is a positive number. So we could say since f double prime changes signs, or changes sign at x equals 3, it is an inflection point. So we found all the critical values and inflection points of our function. So that's a pretty standard example. Again, these problems take a long time when you're doing all of that stuff. You have to not only find the first and second derivative, but you also have to test these things. So one question that's important to ask and think about is, do we really need to test for these inflection points? Is it critical? Does it just switch every time? Well, we do have to test, and how would we prove that we need to test? Well, we can say, what is an example of a value p such that your function f double prime of p equals 0, but p is not an inflection point. Of f. So basically we need to come up with an example of a function and a point where the second derivative at that point is 0, but the second derivative will not change signs there. So a good example that I like to use is just we will consider f of x equals x to the fourth. Has nice easy derivatives to take. So the first derivative, f prime of x, will be 4x to the third. And the second derivative, f of x, will be 12x squared. So if you set that second derivative equal to 0 and solve, it only has one answer, x equals 0. So when you try to test this in the old number line, well, the point is 12x squared. If you plug in any x value that's not 0, you're always going to get something positive. So in region 1, f double prime is greater than 0. Plug in, say, -1, you'd get 12. And in region 2, plug in any number bigger than 0. You could plug in +1, you'd get 12. So the sign doesn't change. So even though the second derivative at 0 is equal to 0, this point is not, or this value is not an inflection point. So therefore, x equals 0 is not an inflection point for f of x. So that's interesting. So it does show that it is important to test these things because sometimes we may not see the signs changing. Okay, so why don't we look at another one where we want to find some critical points and inflection points. So another function to look at that maybe requires some additional derivative skills. So let's say find the critical point and inflection points for f of x equals 2x times e to the minus x. So this is a product of two functions, a polynomial 2x and an exponential e to the minus x. So again, let's kind of try and split this down the middle and see if we can do both parts. So to find the first derivative, we have to use the product rule. So we'll call u 2x and we'll call v e to the minus x. So the derivative of 2x is just 2, and the derivative of e to the minus x, we need to use the derivative rule for exponentials in continuous form, which says it's basically going to be the same thing, but if x is being multiplied by a constant in the exponent, that comes down in front. So this will be minus e to the minus x. Okay, so the first derivative is going to be u prime v, so we have 2e to the minus x and then we add 2x times minus e to the minus x, so that negative sign turns this into subtraction. So minus 2x e to the minus x. So we can set that equal to 0, and it will be helpful to factor here. Factoring is going to be the easiest way to find any zeros. So what can we factor out? Well, we can factor out 2e to the minus x. Both terms have that in common, and we get 1 minus x. So our only answer here is going to be x equals 1. So basically, note that 2e to the minus x is always greater than 0. It's an exponential quantity, so it cannot be equal to 0 there. So the only way that expression becomes 0 is if x is equal to 1. And you can test both sides here in the first derivative, as we saw before. So if you test at 1, we'll end up getting f prime, so region 1 and 2. So sometimes you'll see people just kind of like make the sign, so we end up with positive first derivative on this side and negative first derivative on this side. But just to be explicit, in region 1, f prime is greater than 0, and in region 2, f prime is less than 0. So we can say that a local max occurs at x equals 1. So we get a local max there. Yeah, so really what we're focusing on today is looking at the second derivative. So the second derivative, we need to take the derivative of f prime of x. So the second derivative is going to have two parts. So the derivative of the first term, 2e to the minus x, is just going to be minus 2e to the minus x. So we're looking at taking the derivative of this guy right here. So the first term is easy. The second term has a minus in it, but other than that, if you look at the 2x e to the minus x, that's just what we took the derivative of in the first place using the product rule. So actually the derivative of the second term will be the exact same thing as the derivative we just had. So we'll end up with 2e to the minus x minus 2x e to the minus x. So then we can kind of simplify this second derivative by distributing that negative sign. So we end up with minus 2e to the minus x plus 2x e to the minus x. So we have like terms. The minus 2e to the minus x and the minus 2e to the minus x will be minus 4e to the minus x plus 2x e to the minus x. Okay, so now this is the thing that we want to set equal to 0 and solve. And we're going to do that again by factoring. So when we factor, what can we factor out? Well, we can factor out, again, 2e to the minus x, and we'll end up with negative 2 plus x. So again, 2e to the minus x is always greater than 0. So the only candidate inflection point here is actually x equals 2. If you plug in the 2 for x, negative 2 plus 2 is 0. So the thing inside the parentheses becomes 0, making the entire expression equal to 0. So basically what we have here is we want to test in the second derivative each region to see if it is positive or negative in the second derivative. So what ends up happening, we're going all the way back up, so we can test in any of the versions that we have here. So basically any of these three versions, this is where we want to test either side of the inflection point. So what ends up happening is we end up getting a negative here and a positive here, which basically means that we were concave down in this region and concave up in this region. We can plug in some example points just to see. So e.g., what's an example point from region 1? Well, we can always plug in 0. So anytime you can plug in 0, that's always nice because usually a lot of things go away. So f double prime of 0, if we go back, the e to the negative 0 would just become 1. So we get negative 4 plus 0. So if you plug in 0 into the second derivative, you should get negative 4, which is less than 0. And the first derivative, the second derivative in region 2, we need to plug in an x value larger than 2. So let's plug in 3. And if we do that, the point will not be as nice probably. But so I'm going to do negative 4 times e to the negative third power plus 2 times 3 times e to the negative third power again. And I get 0.10. So I get something greater than 0. So because the sign changes, basically we can say an inflection point occurs. At x equals 2. And that is it for that problem. So again, the process is exactly the same, but just how tricky the derivatives become is kind of what makes the problems more or less difficult. So let's go ahead and look at just one more example where we have to graph something. So this is kind of a create an example type of thing, and sometimes it's good to think about functions in this way. So let's look at this example. So let's say graph f with the following properties. So first, let's say f has a critical point at x equals 4, and we know f prime is negative left of 4, and f prime is positive right of 4. And then let's suppose f has an inflection point at 8, and now we are given some information about the second derivative. F double prime is positive left of 4, or left of 8, and f double prime is negative right of 8. So basically, if we kind of synthesize this information, the first thing tells us the critical point is negative left of 4 and positive right of 4. So we know our function has at least a local min at x equals 4, and from the second piece of information we know the function changes from concave up to concave down at x equals 8. So we have to kind of incorporate both of those things. So you may want to pause your video and try and draw the example function you might think of. That's what I do if you're in class. But there's lots of different ways that you can do this. But basically, we have our two values that we care about, 4 and 8. And we need to make a minimum value here, so let me just make my minimum somewhere down here. And then I need to be changing from an upward U-shape to a downward U-shape at 8. So maybe I have a function that's doing this. I bottom out right there at 4, and then my concavity changes to start moving downward. So I get like that downward U-shape. So that's an example function that satisfies those criteria. But really, if you know some things about the derivative, you really want to think about, okay, what is that telling me in terms of increasing and decreasing and maxes and mins? And then when I have the second derivative, what is that telling me about? Is there an inflection point? And at that inflection point, is the concavity changing? So basically, the first point, this point, basically, and this is our sample graph of y equals f of x. So basically, at this first point, f changes from decreasing to increasing, and then at this next point here, f changes from concave up to concave down. So knowing things about the first and second derivative, in fact, helps us understand properties of the function. That's one of the reasons we're able to sketch graphs of things without plugging in all kinds of points. The derivative and the second derivative are really telling us all sorts of things about the properties of the function. Okay, so we will pick up in the next video with, I believe, so the next section. Let's see, what is that going to include? That's going to include absolute maxima and minima. So a slightly different version from testing the local extrema. So the global extrema invokes what is known as the extreme value theorem, and that applies to any continuous function on a closed interval. So this is Dr. Lennon signing off, and I will talk to you next time.